Hello and welcome to section 6.2. So we're continuing talking about some function operations. In this section we're going to talk about one-to-one functions and inverse functions. Right? So let's look at the definition of a one-to-one function. So a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. Right? So that is, if you have x1 and x2 are two different inputs of a function, then f of x is one-to-one if the output when you plug in x of 1 is always different than the output when you plug in x2 for any values in the domain. Right? So you can check this algebraically, but most often you check this using the horizontal line test. So if every horizontal line intersects the graph of a function at most than one point, then the function is one-to-one. So this is very similar to the vertical line test. The vertical line test was used to check whether it's a function or not. If it does pass the vertical line test, you can use the horizontal line test to test whether it's a one-to-one function. Okay, so basically in a one-to-one function, each x only goes to one y and each y only comes from one x, so there's a one-to-one correspondence. Alright, so let's look at example 1. So we have a couple of functions defined with coordinate points here, and we want to figure out if it's one-to-one. Okay, so here you're looking to see if there are any repeated y values. So if there's repeated y values, then it's not one-to-one. So not one-to-one if you have repeated y values. Right? Because if you do, that would break this condition. Okay? So my y values are 5, 3, 7, 12. No repeated y values. So for each x inputs, they correspond to different y inputs. Okay? So this is yes. It's one-to-one. Alright, let's look at B. Okay, y values 2, 8, 18, 32. No repeated y values, so you go yes, this is one-to-one. Alright, here's an example. Let's say you had 1, 5, 2, 7, 3, 5, and 4, 2. Right. If you look at your list, you have 5 and 5. These are repeated y values. That means f of 1 equals 5 and f of 3 equals 5. These two are not equal to each other, but the y values are equal to each other, right? Then this basically breaks this condition, okay? Because it says if x1 and x2 are two different inputs, then the outputs need to be different, okay? And f of 1 here is equal to f of 3, so it breaks that condition, so this is not one-to-one. Yeah, good. So just so you see what it looks like. Alright, now from a graph you can use the vertical line test. Alright, so horizontal line test. So if you can draw a horizontal line anywhere that meets the graph at more than one point, then it's not one-to-one. Alright, so this does not pass the horizontal line test. For D, you can draw a horizontal line anywhere and it's going to pass the test. So this is one-to-one. Okay. Alright, so now let's look at inverse functions. So an inverse function, so we have a function of x, and its inverse is denoted by this. So this is the inverse of f of x. Okay. So for a function to have an inverse, it has to be one-to-one. for a function to have an inverse, it has to be a one-to-one function. Right? And to find the inverse of a function, you basically flip the domain and range. You flip the x and y values. To find f at -1 of a function, you switch the x's and y's. Basically, you switch the domain and the range. Alright, so you're basically flipping the function over, x's and y's get switched over. Okay? So because that happens, you flip x's and y's, what happens is that the function and its inverse, they're symmetric across the diagonal. So these are, if you graph it, they're symmetric across the diagonal line of y equals x. Right? So the next few examples, you're going to graph the inverse from the original graph of the function. A good way to do it is look at some points on the graph and switch them around, switch the x's and the y's, and graph the new points, and then you'll notice you'll notice the symmetry. Okay, so let's look at this point here. So this is x is -2 and y is -2. You're gonna switch them over, okay, and you get -2 and -2. Okay, so this point is the same; they coincide. Okay, let's look at 0, 1. So this is x and this is y. You're going to switch them. Okay, so you're going to get x equals -1 and y is 0. Right? So we need to graph this. -1 and 0 is here. So let's take it away from here. Okay, so we're constructing the inverse. Right? 1, 0, you switch them over, you're going to get 0, 1, which is here. 2 and 1/2, you switch them, and you get 1/2 and 2, and that's going to be here. Alright, so now let's connect the points. So these connect, and these connect. Alright, and we basically made the graph of the inverse function. So let me kind of draw these points in. Okay, and the function and its inverse will always have the symmetry. So it's, if you look at along the diagonal line y equals x, then you can sort of see the points across from it. So it's the same distance from that line of symmetry to f of x as it is to f of -x. Alright, let's look at this one. Alright, so here we're not given as many points, but we can pick as many points as we want. So we have -2, 1. We also have 0, 0 here. And 1 and -1. And if you want to pick more, you can. So this point right here is like -1 and maybe 0.75. Okay. So let's draw the points for the inverse. Okay, so -2 and 1 are going to become 1 and -2. Okay, so 1 and -2 is right here. All right, so this is the mirror of this one. So if you look across this line, if you connect them, then it should be like the same distance. All right. Now let's do 0, 0. So that's going to be just 0, 0. 1 and -1 are going to switch, and you get -1 and 1, which is here. Okay, so that's the cross there. Okay, so do we have enough? let's do another one. Negative 1.75 is 0.75 and negative 1. All right, so I can see that I need to go like this. And then I'm going to need to go like this. Twist it around. All right, so let's see if I can draw it in red. So this. And then like this. I'm going to try again. Let's make it less thick. Boom. And then boom. All right. So these are points that we draw when we switch the x and y's around. Okay. So again, you're looking at this. You want these two functions to be mirror images of each other across this line. So if this was on a piece of paper and you folded the paper along this line, then it should fall on top of each other. So like this part right here will fall on top of this part right here is going to fall on top of this part. Okay, awesome. All right, so here's a definition of the inverse. Basically, it's what we were talking about before. So you need to start with a one-to-one function, then the correspondence from the range of f to the domain of f is called the inverse function of f, with symbols f to the -1. Basically, you get the inverse by switching the x and y values. All right, so what an inverse does to a function is to reverse the effect. Okay, so basically the inverse reverses f at -1. All right, let's write that down. F at -1 reverses the effect of the f function. Okay, so whatever you did to the input using the f equation, if you apply the inverse to the output, you're going to go back to the input. Okay, so basically, if you take an input value and you plug it into your f of x, okay, so you plug it into an equation and you get some sort of y value as the output. All right, now if you take this and you input it into the inverse equation in here, then you're going to get x again. Okay, so whatever you're doing with the f function is going to be undone by the inverse function, so you go back to the beginning. All right, so you want to verify that the function f of g are inverses of each other. The way you do that is by composing. So if I do f of g of x, the f and g cancel and you get back to the input. And also in reverse, if you do g of f of x, the g of f cancel and you get x. So you compose both ways, and if both ways you get a result of x, then you say yes, there are inverses of each other. Okay, so let's do that. So we want to find f of g of x with these two functions. So we have 3 minus 2, right? And instead of x, we plug g of x, -1/2 x minus 3. And simplify. So we have 3 plus 2 divided by 2 is 1. So 3 plus x minus 3. 3's cancel and we get x. Okay, so good. F cancel g. All right, we gotta go backwards too, because sometimes it cancels one way but not the other. So we have to find g of f of x. So we start with the g function, -1/2 x minus 3. The x gets replaced by 3 minus 2x minus 3. These cancel out. -1/2 of -2x gives me a positive x. Alright, good. So we get results of x in each case. So you say that f and g are inverses, or you can say that g equals the inverse of f. Thanks. Alright, let's look at part B. Same deal. We want to check to see if f of g are inverses by composing them and seeing if we get x. So f of x is defined as x minus 2 squared for x is bigger than or equal to 2. Okay, so the reason this restriction is here is because if I look at just x equals negative 2 squared, this is not a one-to-one function. Alright, so let's move back. Okay, so if I look at x minus 2 squared, this is what this function looks like. If I look at the entire thing is not one-to-one. So what you do is you just look at the part where x is bigger than or equal to 2, so only half of the parabola, and this part is one-to-one. So we're not looking at the entirety of the parabola, just the right half, okay? And then it's a one-to-one function. So let's do f of g of x. So we have x minus 2 squared. The x gets replaced by square root of x plus 2 minus 2. So these cancel out. Square root of x squared gives me x. Good, so f cancels g. Now let's go the other way. G of f of x. We have square root of x, so square root of x minus 2 squared plus 2. Square root cancel the square. X minus 2 plus 2 gives me x. So it works both ways. So I can say that g is the inverse of f. Alright, let's look at part C. Same deal, we're trying to figure out if they're inverses of each other. So f of g of x is x minus 5. The x gets replaced by g of x. And this x gets replaced by g of x. Alright, so g of x is 3x plus 5 over 1 minus 2x minus 5. 2 times g is 2 times 3x plus 5 over 1 minus 2x plus 3. We got to simplify this. Common denominator. We get 3x plus 5 minus 5 plus 10x over 1 minus 2x divided by 6x plus 10. 3 times this, so plus 3 minus 6x over 1 minus 2x. Right, which is going to be 13x over 1 minus 2x. Flip this over, 1 minus 2x over 13. These cancel out. 13x over 13 equals 2x. Wow, it worked that way. Awesome. All right, let's do it the other way. So g of f of x. All right, so in the g function, you replace the x's by f's. So we have 3f of x plus 5, 1 minus 2f of x. All right, let's do the replacement. So this gets replaced by x minus 5 over 2x plus 3. So 3 times x minus 5 over 2x plus 3 plus 5 over 1. 1 minus 2 times x minus 5 over 2x plus 3. Okay. So let's find common denominators. So we have 3x minus 15 plus 5 times 2x plus 3. So 10x plus 15 divided by 2x plus 3. Over, let's multiply that by 2x plus 3, minus 2x plus 10, divided by 2x plus 3. Simplify and flip over. So we get 13x over 2x plus 3 times 2x plus 3 over 13. These cancels. 13x over 13 is x. Good. So G is the inverse of f. All right, they're inverses of each other too. All right. Okay, so now we are going to find the inverse of a function from its equation, find the domain and range of the functions and the inverse, and graph them on the same graph, including that symmetry line, right? So we start with our equation, f of x equals negative 4x. We're going to write it as y equals. Okay, y equals negative 4x. Okay? Then you're going to switch the x's and y's. So switch x and y. Right? So x equals negative 4y. And then we're going to solve for y. Right, so we get y equals negative 1 over 4x. Right, so this is the equation of the inverse. So this is inverse of the function is negative 1 over 4x. Right, so this was the inverse, and this is the original function. Right? You can see the domain of both is all the real numbers. Right? Let's graph them. So negative 4x, y-intercept is 0. Negative 4 is 4 down and 1 across. All right, so this is a straight line going like this. All right, the inverse is negative 1/4 x, same intercept, but it's going down and then down 1 and 4 to the right, or up 1 and 4 to the left. Okay, so this is the inverse graph. Right, and if I draw the line of symmetry, y equals x, we get this. Right, and we can see that they're symmetric across that line. There we go. Okay, let's look at this one. So we start with the equation of f of x, which is x cubed minus 1. And this is a one-to-one function. It's a cubic that's shifted down. So we have this and this and this, and then 2 and 8 goes to 2 and 7. And then negative 2 and negative 8 goes to negative 9. So the original f function is like this. This is f of x. Alright, you can see that it's a one-to-one function, so we can find the inverse. We write y is x cubed minus 1. We switch the x's and the y's. So x equals y cubed minus 1. And then we get y by itself. So x plus 1 equals y cubed. And y is going to be the cube root of x plus 1. Alright, so you can graph this outright, or you can use the graph of f of x to graph it by sort of switching the x and y values. Alright, so you can see that this here at 0, negative 1, it switches at negative 1 and 0. The 1, 0 switches to 0, 1. Negative 1 and negative 2 switches to negative 2 and negative 1. So we have this bit here. Alright, then 2 and 7 switches to 7 and 2. Like this. And negative 2 and negative 9 switches to negative 9 and negative 2. So we have this like this. Right, so this is the inverse. The inverse function is cube root of x plus 1. Alright, so it really, sometimes it's a lot easier to graph the original function and then do the mirror image by switching the x and y values. Right, and here's the line of symmetry. You can see that they're symmetric across that line. Alright, the domains It's a polynomial, so the domain is all real numbers. And this is an odd root, so the domain is also all real numbers. All right, let's look at this function. So we have y, or f of x, equals x squared plus 9. And we are going to restrict our domain to just the positive numbers. So this is a one-to-one function. All right, so we have x squared plus 9 is a parabola, right, that's shifted vertically 9 units. Okay, we want x is bigger than 0, which means we don't want this part. We just want the positive part. Okay, so we're looking at this. All right, so let's find the inverse. Y equals x squared plus 9. We're going to switch the x and the y. X equals y squared plus 9. Subtract the 9. Y squared equals x minus 9. And you have y equals plus or minus square root of x minus 9. Right? Now, when we restricted the domain for x to be positive, we're going to end up with a positive radical. So you have both choices, but the positive choice means this part, and the negative choice means that part. So because we're looking at just the right half, we take the positive radical. Okay, so we can graph this or use the mirror image. So here is 0, 9. We're going to go to 9, 0. And here's 1, 10. We're going to get to 10, 1. And then we draw the square root, which is a square root graph shifted 9 units to the right. Okay, so this is the inverse. And then the line of symmetry is y equals x. And you can see that they're mirror images of each other. All right, so the domain of the original is x is bigger than or equal to 0, because that's how we put it. And the domain of the radical is x is bigger than or equal to 9, because that's what makes the radical work. All right, let's look at this one. Okay, so the original function is y equals 1 over x minus 2. All right, so let's graph this. So we have a vertical asymptote at x equals 2. We have a horizontal asymptote at y equals 0. All right, and this, we have the two branches like this and like this. All right, you can see that this is a one-to-one function. All right, so we're going to switch x's and y's. We're going to solve for y, so let's cross multiply. We have x, y minus 2 equals 1. Divide both sides by x. So we have y minus 2 equals 1 over x, or y equals 1 over x plus 2. So this is the inverse function. Okay. So when we switch our x's and y's here, we're switching the vertical and horizontal asymptotes. Okay, so this y0 becomes a vertical asymptote at x equals 0. And you can see that matches with this equation. And the vertical asymptote at x equals 2 becomes a horizontal asymptote at y equals 2. And you can see that matches because this is vertically shifted, right? And then we draw this part here and this part here. Right? And if we draw the line of symmetry, right? I didn't draw that well. They should intersect over there. Let's see if I can do a bit better job. We have this, and then these ones. All right, let me draw it like this. There you go. Okay, so they're mirror images of each other. All right, so let's look at the domains. So the domain of the original is all the reals except for x equals to 2. And the domain of this one is all the reals except for x equals 0. All right. Okay, so here we're going to find the domain, the inverse function, but we're not going to graph it because these become more complicated. So we're just going to write the function in terms of y, 2x over 3x minus 1. Switch the x and y. So x equals 2y, 3y minus 1. Notice that everywhere you see x's, they get replaced by y's. Right? So we're going to cross multiply. X times 3y minus 1 equals 2y. Let's distribute this. Actually, let's divide by x. So 3y minus 1 equals 2y over x. That's not going to help. I was trying to be clever, and that never works. All right, we're going to distribute the x. We have 3yx minus x equals 2y. Our goal is to get y by itself, so we're going to subtract 2y from both sides and add x to both sides. Now both these terms have y, so we're going to factor them. Y times 3x minus 2, and then divide both sides by 3x minus 2. So y equals x over 3x minus 2. Right, so this here is the inverse function. Alright, and it's asking for the domain and range of the original function and the inverse. Okay, so for the domain here, I can see that it's all the reals except for 1/3, because we have a vertical asymptote here. And the range is going to be all reals except for y equals 2/3, because we have a horizontal asymptote in that case. Okay. Actually, a better way to find the range is to, let's find the domain of each. Okay, so find the domain of this, we're excluding 1/3. We find the domain of the inverse, you can see that is the reals excluding 2/3. Sometimes it's hard to find the range of a rational function by just looking at the equation. You kind of have to graph it sometimes. All right. But I know that because I'm switching the x and the y values, the domain of the function becomes the range of the inverse. So the range here is the same as the domain there. So everything except 1/3. And the range of this one is the domain of this. So all the reals except for 2/3. Okay, so that's a really good way of finding the range of rational functions. All right, let's look at this one. So write it in terms of y. Y is 2x minus 3x plus 4. Switch x's and y's. So x equals 2y minus 3y plus 4. Cross multiply. So x times y plus 4 equals 2y minus 3. Let's distribute the x. xy plus 4x equals 2y minus 3. And move things so y and x's, y's go together. So xy minus 2y equals negative 4x minus 3. Factor out the y. And then divide by x minus 2. So we get y, or the inverse, is negative 4x minus 3 over x minus 2. Okay? Cool. So now we're going to find the domain of each. So the domain of this one is all the real numbers except for x equals negative 4. the domain of this one is all the real numbers except for x equals to 2. And then for the range, you switch them. Okay, so the range here is this domain. And the range of this one is this domain. Right? So that's the definition of an inverse, is you're taking the original function and you're switching x's and y's, replacing x's with y's, which means you're replacing the domain with the range, and vice versa. All right, let's look at this one. We have f of x equals x to the 3/2 plus 5, which is like square root of x cubed plus 5. So y equals square root of x cubed plus 5. Switch x's and y's. So x equals square root of y cubed plus 5. So let's solve for y. So subtract the 5. And then we have to square both sides. And we get y cubed equals x minus 5 squared. And then take the cube root. So cube root of x minus 5 squared, or x minus 5 to the 2/3. All right. Okay, let's see what the domain here is. So the domain of this one, we need this to be positive numbers. So we need x to be bigger than or equal to 0. All right, the domain here, this is a cube root, so it doesn't matter what values of x we plug in. It could be positive or negative. So this is all real numbers. Okay, so now switching the domain and the range. The range of this is x is bigger than or equal to 0, or y. Right? And the range of this is all real numbers. All right, and that's it for this section. Excellent.